Minimizing correlated failures in distributed systems. This is an architecture lecture blog post from the Amazon Builders Library by Joe Magaremov. Minimizing correlated failures in distributed systems. I think years ago, just as I was starting my career, I was at a small company working on a web application that allowed consumer goods companies to analyze their sales trends. The application used a three-tier architecture, a front-end written in Java, a back-end written in C++, and a relational database to store state. All three components ran on a single server. Of course, now we wouldn't be happy with such an architecture because it contains a single point of failure, because everything was on the same server. However, back then this was a common setup. If the server failed, we worked really hard to fix the problem or restore the application on a different server. To minimize downtime during such events, a whole ecosystem of servers with redundant and hot swappable parts, including CPUs, thrived. Some of these servers had price tags that rivaled the value of our small company, so the replacement parts were actually hardware that they replaced in case of failures. A few years later, I joined Amazon and was exposed to a very different approach of building systems. By that time, Amazon was well on its way to adopting service-oriented architectures and distributed systems. By embracing distributed systems, a rapidly growing online store could deal with ever-increasing scale. However, there was another important benefit. By running on multiple servers, a service could be architected to continue operating even if some of these servers fail, while using relatively inexpensive commodity servers. Achieving fault tolerance. To achieve fault tolerance, a typical Amazon service at that time ran on multiple physical servers behind a load balancer that distributed incoming requests among those servers. So this is simpler. You have multiple servers behind load balancers. To deal with server failures, the load balancer sent a periodic health check, typically a small HTTP request to a well-known URL, to each server. If any of the servers failed to respond to several times in a row, the load balancer took that server out of the consideration for future requests. To learn more, check out David Janczek article or health checks in this Amazon Builders Library article implementing health checks. To avoid the load balancer itself becoming a single point of failure, two load balancers were arranged into a primary and secondary belts. So also the load balancer are becoming a primary and secondary, and the domain name system was used to fail over the secondary if the system needed persistent storage. A similar technique was used to set up a pair of replicated relational database with an active primary and a standby secondary. The following diagram shows an example of this architecture. So we have primary load balancer, the DNS would go to the secondary in case of failure. We have a set of servers behind the load balancer, and we have a primary database that is replicated to a standby database. Now we use load balancers like application or load balancer or network load balancer, and storage services like Amazon DynamoDB to provide scalable and fault-tolerant building blocks for our services. But the core principle remains unchanged. If we can architect our system to run on multiple redundant servers and continue to operate even if some of those servers fails, then the availability of the overall system will be much greater than the availability of any given server. This follows from the way probability compounds if it's independent. For example, if each server has a 0.01% chance of failing on any given day, then by running on two servers, if they are independent, the probability of both of them failing on the same day is 0.0001%. We go from somewhat unlikely event to incredibly unlikely event. The problem with correlated failures. However, we only get the benefit of compounded probabilities if the failures are uncorrelated, that is, if individual failures are always independent. Unfortunately, in the real world, that isn't always the case. A single underlying cause can trigger multiple failures. A correlated failure actually happened in my house. A few years ago, we replaced all the built-in cabinets. Each cabinet used a pair of plastic brackets like the ones in the following images, to attach its front, to attach, oh my god, to attach its front panel, we used these cabinets without any problem for more than a year. After that, the brackets in the first cabinet broke. A week later, the brackets broke in the second cabinet. Then in the third and in the fourth, within 3 months, the brackets had broken. Every cabinet in our house needed to be replaced. To this day, we don't know what caused all the brackets to fail around the same time. It could have been a production defect that affected the entire batch, or perhaps the installer chose the wrong bracket type that wasn't related for the load it had to bear. All the failures could have been caused by the moisture level in our house, or the way our family used these cabinets. The important fact was that an unforeseen factor created condition where instead of failing at independent times, the bracket suffered a correlated failure. We say that the system suffers a correlated failure when multiple independent components fail due to the same underlying cause. For example, if we have a shutdown of electricity in the whole building, then this is the same problem that causes all the semi-independent components to fail. Those causes can vary in complexity and sometimes, as in the case of our failed cabinet brackets, can be hard to predict. It's worth noting that there is a similar failure mode called cascading failure, where a failure of a single component causes an increase in load in the next component, causing it to fail. Yeah, so one component fails, then the next component has more load, causing it to fail, and so on. This article focuses on minimizing the risk of correlated failures. However, avoiding cascading failures can be just as important when building resilient systems. Luckily, the reliability of our house didn't depend on these brackets, and the impact of multiple cabinet brackets failing at the same time was at most a minor inconvenience. But similar risks of correlated failures can exist in distributed systems as well, and when they do, they eat away the availability gains we achieve from redundancy. Some familiar causes of correlated failures include issues with data center power, network, and cooling. A failure of any of these components can impact all the servers in that data center. At Amazon, we also learned that without a lot of dedicated engineering work and careful attention, common infrastructure dependencies like DNS can cause correlated failures as well. There's a popular joke among infrastructure engineers: it wasn't DNS, it definitely was DNS, it was DNS. But more subtle risks of correlated failures exist as well. A batch of hardware components could have the same latent manufacturing defect, or a single operator action could have an impact on multiple servers. As hardware components age, failure probabilities increase as well, making it more likely that multiple servers will fail at the same time. These factors work against the distributed system, increasing the probability of multiple simultaneous failures, and thus reducing the effectiveness of redundancy in our architectures, using regions and availability zones. At Amazon, we approach reducing such risk by organizing the underlying infrastructure into multiple regions and availability zones. Each region is designed to be isolated from all the other regions, and it consists of multiple availability zones. So we have regions, and within regions we have the availability zones. Each availability zone consists of one or more discrete data centers that have redundant power, network connectivity, and are physically separated by a meaningful distance from other availability zones. Infrastructure services like Amazon Elastic Compute Cloud EC2, Amazon Elastic Block Store EBS, and Elastic Load Balancing ELB, and Amazon Virtual Private Network Cloud VPC run independent stacks on each availability zone that share little to nothing with other availability zones. Because any change brings with it a risk of failure, infrastructure teams configure their continuous deployment systems to avoid deploying changes to multiple availability zones at the same time. To learn more about our approach to safe continuous deployments, read Claire Luigi's Lugori article on automatic and safe hands-off deployments on the Amazon Builders Library. Separation of infrastructure into independent availability zones allows services teams to architect and deploy their services in a way that reduces risk that a single infrastructure failure will have an impact on the majority of the fleet. By the mid to late 2000s, a typical Amazon service user architecture looked like this. So we have here two availability zones. We have an active load balancer. Probably there is also an inactive one by the DNS. It goes to multiple servers. And then it goes to a single here, DynamoDB. Or a global DynamoDB that you don't care how it's being distributed. We found availability zones to be so powerful at reducing the risk of correlated infrastructure failures that when Amazon EC2 went public in 2008, availability zones were a core feature. These days, AWS customers and internal service teams alike use availability zones to build highly available applications on top of EC2. My colleagues Becky Weiss and Mike Furr wrote about getting the most out of the availability zone in the Amazon Builder Library article, static stability using availability zones. Non-infrastructure causes of correlated failures. However, we found that in most systems, the physical infrastructure isn't the only factor that can cause correlated failures. We discovered that any action performed by an operator or any tool that can act on multiple servers at the same time has the potential to introduce correlated failures modes into the system. Early in my career, when I worked on operational issues, it was not uncommon to execute a command on all the servers in the fleet in parallel. For example, to grep for a specific log line, or to adjust some operating system parameters. These days, we know that, however unlikely, performing such actions and using tools can introduce correlated failures modes into the system. This is because if anything goes wrong, it will impact every server at the same time. Whenever we build with and use such operational tools and practices, we always make sure to introduce velocity controls and feedback loops. This ensures that in the unlikely event that something goes wrong, it will only impact a small percentage of the servers, reducing the blast radius. However, we don't stop there. We also make sure that our operational tools and practices takes availability zone into account. While such operational tools are not directly related to the underlying infrastructure boundaries, we know that our services are architected to withstand an availability zone failure, thus giving our teams a well-understood and practiced fault boundary. For example, a system responsible for automatically patching our servers has both built-in velocity controls and fail-safe mechanism. Velocity controls that take it, first do a change to the first server, make sure everything is okay, then 2 servers, then 4, or whatever. Velocity. But it also never operates on servers from multiple availability zones at the same time. However, we don't stop at availability zone. At AWS, it's becoming a common practice for services to adopt cellular architectures. Instead of operating a single stack per availability zone or region, we subdivide a service into a set of identical and independent partitions called cells. Among other benefits, cells allow us to limit the impact of unforeseen problems or failures. This is like subclusters in an availability zone. For services that adopt cellular architecture, we make sure that our operational tooling and practices take cells into account and avoid touching multiple cells at the same time. Reducing correlated behaviors. Even with all these precautions, most distributed systems still have one important correlating factor. Each server in the system runs the same exact software. This situation reminds me of a favorite video game I used to play when I was growing up, Lemmings. The premise of the game was that you controlled a group of adorable little creatures called lemmings who were traversing landscape filled with obstacles and deadly traps. The catch was that lemmings lacked free will, so each lemming moved in a predictable algorithmic path. When faced with an obstacle, a lemming would turn around. When faced with a cliff or a trap, a lemming would mindlessly walk straight ahead. And because every lemming followed the same algorithm, if one lemming perished, so did the rest of them. As a player, you had to use the features of the terrain and small number of tools to safely guide a group to the exit. Although most distributed systems run software that is significantly more sophisticated than the AI in control of lemming, they can still suffer similar fate. For most distributed systems, every server in the fleet runs the same exact software with the same limits and failure modes. Load balancers and other work distribution mechanisms tend to do a really good job of evenly distributing the load across all the servers, which is exactly what we want them to do. However, when a software bug or a load-related failure causes one of the servers in such distributed system to fail, this same cause can also impact the rest of the fleet at the same time. Early in my career, one common example of such failure was running out of open file descriptors. In many operation systems, a file descriptor is a data structure that represents an open file or network socket. There is usually a limit on how many such file descriptors any single process can open at a time. If that limit is exceeded, it can cause the application to fail in unpredictable ways. If incoming load causes the software running on one of the servers to run out of open file descriptors and fail, an evenly distributed load would frequently cause the other servers to experience the same fate. These days, applications are not likely to run out of open file descriptors thanks to many hard-won lessons. And the ample memory present in modern servers, most systems defaults to a high enough file descriptors limit to make running out of impractical. Still, other limits, behaviors, and even bugs can exist, and they can introduce correlated failures modes into the system. Where possible, one powerful approach to minimizing risk of correlated failures that we like to use is shuffle sharding, a workload isolation technique that makes sure no two servers in the fleet see the same exact workload. That way, if anything but this handles only the case that it's the workload that's causing the bug. That way, if anything about its workload causes a server to fail, it is unlikely to impact all servers in the fleet. To learn more, go to the Amazon Builder Library article called or wrote about shuffle sharding, workload isolation using shuffle sharding. Correlated behaviors can be another challenge for redundant systems. This reminds me of another experience I had at home. Several months ago, I was working from home and my home internet service provider ISP suffered an outage in my neighborhood. I had several important meetings to attend. Luckily, I had a cellular service from a different provider and was able to quickly set up a Wi-Fi hotspot on my cell phone and tether it to my laptop. To my surprise, the cellular service began experiencing a slowdown as well. I later found that many of my neighbors who were also working from home, if you are reading this article at a later date, this was during the time of COVID-19, there were many people in North America who work from home, had the same ID, and the cellular network in our neighborhood simply wasn't ready to handle all that additional load. In this situation, the correlated behavior of the larger system ISP customers failing at the same time caused the failure in the second completely unrelated system, the cellular network. Similar risks exist in distributed systems as well, where it's possible to end up in a situation where a large number of clients change their behavior at the same time, creating a highly correlated spike in load. Changing a human behavior is really hard. However, changing the behavior of computers is easier. Where possible, one technique we like to use at Amazon is reducing jitter, which is adding a small amount of randomness to common behaviors and limits. Our teams are on the lookout for parts of the system that can result in a highly correlated behavior. So if you have a limit of a rate limiter, for example, then you add some jitter to it. And they use jitter to reduce such risk. Here are just a few examples of using jitter to reduce risks of correlated behaviors. Varying the frequency at which each server runs housekeeping jobs. Adding a small amount of randomness to the delay before a failed API is retried. To learn more about this, go to Mark Booker Amazon Builder Library article on adding jitters. If the system contains mode shifts, example refreshing its state from a remote data store, varying the threshold at which such mode shift occur, varying expiration times for short-term credential secrets, varying cache time to leave TTL across servers, where applicable, adding a small amount of variability or to various resources limits such as Java Virtual Machine, heap and connection pool sizes. I want to know that one challenge with using Jitter is that it can make debugging, the overall system more challenging, and testing. If the behavior of the application varies across servers and time, bugs and other failures can become harder to reproduce. We found that one approach to manage that downside is to seed the random function that is used to add jitter with a well-known parameter like the name or the IP address of the server. That way, its server will always use consistent and predictable values for its jitter, yet be different from other servers in the fleet. Conclusion: redundancy has been instrumental in helping us build highly available systems, even while using relatively inexpensive hardware components. By architecting our systems to run on multiple servers, we can make sure the system remains available even if some of those servers fail. However, both known and hidden factors can introduce risks of correlated failures, which eat away the benefits of redundancy in distributed systems. Some example factors that could cause correlated failures are infrastructure components like power, cooling, network, common dependencies like DNS, operator actions that touch every server, like deployments, every server in the fleet having identical behavior, and resource limits. At Amazon, we look at ways to reduce such risks. Availability zones are one such powerful mechanism. By organizing infrastructure into independent locations that share as little as possible with each other, we give our own teams and customers powerful tools to improve availability of their services. Beyond that, our service teams look for techniques like shuffle sharding and jitter. Shuffle sharding means that you load balance the traffic in a little shuffly way and not the same exact way, and jitter to reduce the risk of single software problem impacting all the servers in the fleet.